Welcome and thank you for attending my talk on the nano-arcsecond resolution of accreting black holes using gravitational microlensing. My name is Henry Best and I'm a student at the CUNY Graduate Center of New York. First, we should outline the problem. A quasar is a supermassive black hole which is actively accreting gas. This accreted gas becomes extremely luminous and observable even at cosmological distances. However, due to these distances size, we cannot resolve the inner structure traditionally. Gravitational lensing occurs when there's a galaxy that lies between us and the quasar. It produces multiple magnified images, and these images then fluctuate in time due to individual stars' lensing effects. This is the gravitational microlensing which we focus on today. A high magnification event occurs when a caustic curve crosses over the inner accretion disk. A wealth of information can be extracted from this event, and our group hopes to perform follow-up observations of such. We expect the Vera Rubin Observatory to identify hundreds to thousands of these events over its survey. The model we use is a Shakura-Tsanaev thin disk with many parameters. Shown on the right is an image of the disk, clearly asymmetric due to relativistic beaming and lensing up from the central supermassive black hole. The ISCO, or the innermost stable circular orbit, is clearly visible here. The model we present today is that of a 10 to the 8th solar mass, non-rotating supermassive black hole, accreting at an Eddington ratio of 0.15. I have a light curve plotted here, which shows the ISCO crossing event as we approach the peak of the light curve, as well as the asymmetry that came about using such an asymmetric disk. Now we ask if we can accurately measure this ISCO size. We create mock data using varying degrees of Gaussian noise up to 5%, as well as a wide range of cadences. Plotted here is a 2% uncertainty in photometric uncertainty, and a 4-hour cadence. We then fit a spline fit in order to smooth the curve, and we see that we seem to have lost the ISCO crossing. However, it's still contained in the information held in the second derivative of this plot. This negative double peak structure is indicative of the crossing event. Now I'd like to discuss the input error and the preliminary results. In our first plot at the bottom left, I have varying degrees of input error, as well as the mean ISCO found, or the mean time found for the crossing event. And this, based on our parameters input, corresponds almost directly to the number of RGs of the ISCO itself. We see that at very low error, there is very small variance in the standard deviation. And as we approach 1, we have 1% error. We have increased standard deviation. After that, it increases greatly and even deviates from the measurement we expect. So we know that this is where our assumptions sort of break down. The cadence is also important, so we should look at that. In all of these plotted here, we have a 1% input error. However, the cadence is varied. So with a short cadence, which means many measurements, we get a very concise data set of very slightly around, it's within 1 standard deviation of the 3 days expected. However, as we increase, we see that the standard deviation increases greatly. We also, again, see the small deviation from our expected mean value. However, that is expected when the mean value is 3 days and we're only observing it twice in those 3 days. In the future, we can work with light curves at multiple wavelengths. So if we were to use the same data with multiple wavelengths, we can get multiple observations at each time, leading to a better value for the mean of the ISCO. We can introduce error which mimics a physical telescope as opposed to that of just random Gaussian noise, to produce a more accurate simulation. And we can expand the work done to a wider range of caustic structures, such as cusp or double crossings, as well as look beyond the accretion disk physics of the Shakura-Tsanaev model. Thank you for viewing this talk. If you'd have contact me for questions or comments, my information is down below.